Welcome back to a course on measure theory and integration. In this lecture, we are about to see the concept of measurables sets. In Lebesgue measure, we are going to see the concept of measurable sets in this lecture, right? So, before formally starting this measurable sets, I would like to recall something from the outer measure. So, outer measure has four virtues. That is, first of all, it is defined for all sets of real numbers. And the next one is outer measure of any interval is the length of the interval. And outer measure is countably subadditive. And the fourth one is outer measure is translation invariant. So here, if you notice, this outer measure fails to be countably subadditive. Sorry, countably addictive, right? So why should we go for the countably additiveness, even if it is not finitely addictive? Okay, so we are able to produce. Okay, there exist disjoint sets A and B for which m star of A union B is smaller than m star of A plus m star of B. This is happening in general. Okay, they are not saying it has to happen for all the sets, but there exist here. If you notice the terminology that I use, there exist disjoint sets A and B for which this happens to be true, right? This one, okay, it means there is some fundamental defect because of which it is happening. Some people identify sigma algebra of sets as the Lebesgue measurable sets. Sigma algebra of sets contains all intervals, all open sets, and when we collect the sigma algebra, some people treat the sigma algebra itself as the Lebesgue measurable sets. That is where the problem occurs, right? So the proper definition of a measurable set is given to be a set is said to be a measurable set for any set if the equality holds. Okay, that is the outer measure of any set is same as that of the outer measure of A intersection with E plus outer measure of A intersection with E complement. Okay, this definition was given by the Constantine Carathéodory. Okay, this is the person who gave the definition of this measurable set. Okay, so with which we are about to prove something. So that is A, the set A is assumed to be measurable and B is any disjoint set from A. So it means what? A intersection B is empty, right? So now A is given to be measurable. So it means what? M star of any set is M star of that any set intersection with E plus M star of any set intersection with E complement. In the place of E, we will have A. Okay, in the place of any set, what are we going to do? So with which what are we trying to prove? Here in this inequality, that is in equation 1, we have the strict inequality, right? So the strict inequality may be replaced with the equality if the set is measurable. That is what we are trying to prove now. So we'll have to involve the set A and B inside it. So when we have to involve A and B and we are trying to prove the equality in equation 1, so in the place of any set we are going to take A union B. So here we will have A union B. By the definition, this inequality holds true for any set A. So there is no issue in taking A union B. Now, if you consider what is A is subset, B is subset, they are disjoint. Okay, so you can here see A union B is this shaded region. Okay, when you make the intersection with A, you are going to get only A. So this is M star of A, right? And if you identify your A complement, this is your A complement. Now you will have to make the intersection of A complement with A union B. So you are going to get only B. So that is M star of B. Right? So what did you get here? So if one of A and B is measurable, then outer measure of A union B is M star of A plus M star of B. Right? So next we are going to make some note here. We can write A as A intersection E union A intersection E complement. By the subadditivity, it clearly follows that M star of A is smaller than or equals M star of A intersection E plus M star of A intersection E complement. Right? So this holds trivially for any set A and E. Okay, here the terminology of measurability is not at all involved. So with which what can we say about the measurable sets is that a set E is measurable. If you have to talk about the measurability, what happens? This holds trivially. Okay, even the set is not measurable, then this inequality holds. So the reverse inequality has to hold. That is M star of A is bigger than or equals M star of A intersection E plus M star of A intersection E complement. Okay, and one more thing, this inequality holds trivially if M star of A is infinity. Okay, that is evident. Yeah, you can just have a look at these things and understand what's happening, how it's happening here. Right. So now let us come. Let us see few propositions. any set of outer measure 0 is measurable. In particular, any countable set is measurable. Okay, first of all, let us prove the theorem for a set with outer measure 0. Okay, let E be any set with outer measure 0. That is m star of A is 0. Right? And again, let us take A be any set. Now, A intersection E is a subset of E. Am I right? Yeah. Therefore, m star of A intersection E is smaller than or equals m star of E, which is assumed to be 0. Okay. We know that m star is a non-negative valued function. This forces m star of A intersection E is 0. Right? Now, we have A intersection E complement is a subset of A, with which what we have is outer measure of A intersection E complement is smaller than or equals outer measure of A. So this quantity I may write it as m star of A is bigger than or equals m star of A intersection E complement. Okay, so this it still retains to be m star of A intersection E complement plus 0. Okay, the 0 is to be replaced with what? M star of A intersection E. Right? So what we proved here is m star of A, which is bigger than or equals m star of A intersection E plus m star of A intersection E complement, and this completes the proof. So with which we come to a conclusion that any set of outer measure 0 is measurable. Okay, here in particular they have given that any countable set is measurable. Okay, so we have already proved that any countable set has measure 0. So m star of C is 0 for any countable set. So this one we proved already. Okay, you can revisit them and you can just prove this, right? Suppose if you are asked to prove any countable set is measurable, first of all you will have to prove any countable set has measure 0. Then you will have to proceed with this proposition, right? Now let us move to the next one. That is the union of finite collection of measurable sets is measurable. Okay, in order to prove that union of finite collection of measurable sets, what is the ideology that we are going to implement here? First of all, we will take two measurable sets, namely E1 and E2, and we prove E1 union E2 is measurable, right? Next, we just extend this ideology. That is what you can make use of the induction on the value of n. Okay, So prove for two sets and assume this happens to be true. Uh, assume your union I runs from 1 to n minus 1. Ei is measurable and try to prove when you include n. Okay, you consider till n minus 1 as a single set and consider en alone different set, and you can just blend these ideologies that we have done for the two sets. Okay, so I'm let me try to give you those ideologies as well. Okay, first let us start the proof. Let's e1 and e2 be any two measurable sets, and a be any set. Okay, now I am going to make use of the measurability of e2. Since e2 is measurable, we write outer measure of a intersection e1 complement. Here we may have any set, right? So we are choosing this set, that's it. So this is equal to m star of a intersection e1 complement intersection with e2 plus m star of a intersection e1 complement with e2 complement. We mark this as equation 1, right? And we will have to express something for a intersection e1 union e2, right? Because we'll have to prove the measurability of this quantity, that is the e1 union e2. Okay, so for which let me try to give you the ideologies using some diagram. Okay, so let this be the whole set, okay, in which I have chosen this is to be my e1, and let this be my e2, and let this be my a. Okay, this is my a, this is my e1, and this is my e2, right? So here, first of all, what should I do? I'll have to find e1 union e2, and I'll have to make intersection with a. So only this portion I would get, am I right? So only this portion I'm going to get. Okay, this is my resultant requirement. Next, what should I do? I am saying that it is same as that of a intersection e1 union a intersection e2 intersection e1 complement. That is, so first of all, okay, let me do that thing in a green color. A intersection e1 means I am going to have this portion. Okay, so let me do this side. Okay, this portion I am going to get. Next, I will have to collect A intersection E2. When I collect A intersection E2, I would get this portion, as well as this portion will also be covered. But when I make again this intersection with E1 complement, I will be left with only this part, right? So initially from the diagram, you know that what is the requirement, and this is that one we disjointify and write that as a union of two disjoint sets. Okay, what we actually tried and found here is that we disjointified them. Okay, if you directly write these things, you would get a intersection e1 union a intersection e2, but you have to disjointify them, which means you will have to remove the points that is already present in the first set. So that is why you just made an intersection with E1 complement so that the common points are not included, right? So either you can write it from the diagram or you just have the idea of writing A intersection. Okay, this is the ideology. Okay, this is not a part of a proof, but how to write this one, I am giving you the ideologies here. That is A intersection E1 union E2. By the laws of set theory, you get this to be A intersection E1 union with A intersection E2. Okay, so basically you have two sets. Basically you have two different sets. This is one set and you are making the union of other set. You will have to remove the common points. So for which what you are taking is that you just take the complement and make its intersection with the other set. So the common points are omitted from this. That's it. Okay. Now let us get back to the proof. So now what is outer measure of A intersection E1 union E2? By the subadditivity, this is smaller than or equals m star of A intersection E1 plus m star of A intersection E2 intersection E1 complement. Okay, I mark this as equation 2. Now I will have to estimate m star of A intersection E1 union E2 plus m star of A intersection E1 union E2 complement. Okay, so I'll have to estimate these things. Fine. So this is what this is m star of A intersection E1 union E2 with m star of this is A intersection E1 complement intersection with actually when I make a union this quantity union A intersection E2 complement. Okay, I am just applying a set theoretic class to this and get this quantity though. So this is nothing but simply m star of A intersection E1 union E2 plus m star of A intersection E1 complement intersection E2 complement, if I'm not wrong. Yeah, so this is the quantity I'm going to get. Okay, what is my A intersection E1 union E2? That is smaller than or equals m star of A intersection E1 plus m star of A intersection E2 intersection E1 complement. Right? And I have this quantity, that is m star of A intersection E1 complement intersection E2 complement. Okay, this is from 2. Right? So now what shall we write about these things? That is A intersection E2 intersection E1, A intersection both the complements. That is from equation 1 we shall write this as m star of A intersection E1 is there as it is plus m star of A intersection E1 complement. This is by equation 1. Right? So what did we prove? So this is happening to be true. Okay, we shall write this as m star of A intersection E1 union E2 plus m star of A intersection E1 union E2 whole complement is smaller than or equals I write it as outer measure of A. It's because E1 is measurable. Here I am making use of the measurability of E1, which means what? M star of A equals M star of A intersection E1 plus M star of A intersection E1 complement. So I am just making use of the measurability on A and I get this quantity. So this is what we get, the actual inequality that we need, right? So this proves E1 union E2 is measurable. Okay. Uh, Now you just assume union I runs from 1 to n minus 1 ei is measurable. Proof union I runs from 1 to n ei is measurable. So the hint that I can give you is, take union I runs from 1 to n minus 1 ei as some en minus 1 prime and en, and do the same argument. Okay, so do the same argument that we have done here, and that would give you the result that finite union of measurable sets is measurable. Okay, this implies finite union of measurable sets is measurable. Okay, so I'll leave this proof as an exercise to you people. Okay, try to complete it. The next result that we have is A be any set, and we have a disjoint collection of measurable sets. Then we'll have to prove A intersection this union is equal to the sum of the individual measures. Okay, hope it is evident from the proposition statement itself, right? So how are we going to prove this? In order to prove this, we prove this by the induction on n. Okay, let us start the proof. The proof is by induction on n. When n is 1, we have m star of A intersection only E1, which is equal to m star of A intersection E1. So in this case, the proof is obvious. So we assume that the result is true for n minus 1 sets. That is m star of A intersection union I runs from 1 to n minus 1 ei is equal to summation I runs from 1 to n minus 1 m star of A intersection ei. Okay, therefore now we consider A intersection union I runs from 1 to n ei Okay, this quantity as I just make intersection of this quantity with En. So what would I get? I would simply get this to be equal to A intersection E1. Okay, why is it so? Because we initially assume the collection EK is a finite disjoint collection. So the sets inside this union are all disjoint. Okay, when you make an intersection of this quantity with only one set, I would be left with only the particular set in which I'm along with which I take the intersection. So this is going to be A intersection En, right? Also, A intersection union I runs from 1 to n e I intersection with En complement would be En complement. Okay, all these are disjoint sets, right? So here I included En and I take an intersection with En complement. So what would be there? That En portion won't be there, right? So this is nothing but A intersection union I runs from 1 to n minus 1 ei, right? Here if you notice very clearly, uh, are A intersection En and A intersection union I runs from 1 to n minus 1 ei are disjoint sets, right? Now let us prove the requirements. That is, consider m star of A intersection union I runs from 1 to n ei as m star of A intersection union I runs from 1 to n minus 1 ei plus m star of A intersection En. Why is it so? Because we consider this entire union as a union of only two sets, and we assume the result is true for n minus 1 sets. So we split and write like this, and this is nothing but summation I runs from 1 to n minus 1 m star of A intersection ei plus this is simply m star of A intersection En, and this happens to be what? Summation I runs from 1 to n m star of A intersection ei, right? And this completes the proof. Now you may ask me, we have just proved the result for n is equal to 1 and we assumed it is true for n minus 1 sets. What is the necessity that this n has to be bigger than 2? What if n is equal to 2? Right? You may ask me like this. Okay. Coming back to the proposition statement, A is any set and EK be a finite disjoint collection of measurable sets. Right? So for the finite collection, we are talking these things. Now, coming back to the definition, here we have proved this thing, right? So the equality is preserved for two sets, even if one set is measurable. With this ideology, you can easily prove the result holds true for two sets. Okay, you can just go with this proof, or if you need to prove for two different sets, yes, of course, you may try it out and you can just incorporate that proof into here. Okay, so in at this place, okay, actually I am leaving that as an exercise to you. Exercise is, you will have to prove the result for n equals 2. So only when you prove for n is equal to 2, you can incorporate that result to complete this proof. Okay, with which I conclude this lecture, and in the upcoming lecture we are about to see the collection M of measurable sets is a sigma algebra. Thank you.